Okay, welcome to Stat 479, Lecture 10. So today we're going to kind of wrap up our second key module, which is generalized linear models and convex optimization. And so in particular, I'll go through some of the statistical analysis aspects of it, which is the fourth component of our framework. And then I'll also give a brief overview of what we've done before. And so that should put you in a position to address any questions related to homework 2. And so that's each homework will kind of cover one of the modules. So there'll be kind of probably four key modules, and we're going to get to the end of the second one today. And I'll start to introduce the third module, depending on how much time we have, which is on like kind of regularization when we're dealing with multivariate statistics. So just to remind everyone, so for generalized linear models, what we've done so far is really focused on the first three components of the framework. So in terms of the framework, we talked about the data, which is again supervised data. So you have p covariates and a single response. And then there's n samples of these that are, we'll see later, independent. Useful notation is to combine each, for each sample, just combine the p covariates into a single vector. So this is a p-dimensional vector representing each of the p covariates. And then you have that, each one kind of goes with a response. So each of the n data points can be thought of as a p-dimensional feature vector, x of I, and a response, which is just a one-dimensional R vector. And the idea behind generalized linear models is that we want to account for various different data types. So the Y could be kind of any general data type. Again, so now the model, which we spent almost 2 lectures on really, which is the generalized linear model, is that, yi is related to the covariates through some distribution, and then and then the covariates multiplied by p parameters, or if we take a dot product of the covariate with p parameters. So b is a p-dimensional parameter vector, and so the key thing is that the distribution p is a natural parameter exponential family distribution. So p has the following form, which we've seen at various points. Okay, so here we have kind of this general form, which is that p has this base measure or base distribution h of y, the natural parameter theta, some sufficient statistic t of y, and that's typically been y in all the examples we've seen. So I've often just replaced t of y with y. It doesn't always have to be y, but in kind of the examples that we've seen, t of y, the sufficient statistic is just y. And then this very important function, which is the log partition function, a of theta. So remember that we kind of covered some of the key properties of a. So a was the log partition function, and then we sort of learned that a is a strictly convex and differentiable function. So strict convexity means that the double derivative or the Hessian is always positive for all choices of theta. And so we have that the expectation of the sufficient statistic is a prime of theta, and then the variance is the double derivative or a double prime of theta. Okay, and then the last lecture and a bit of the lecture before focused on estimators or algorithms. So remember that we focused on the maximum likelihood objective function, which we're trying to minimize, or in particular, we're trying to minimize the negative log likelihood objective, because if we maximize the likelihood, that's equivalent to minimizing the negative log likelihood. And we end up with this kind of form where we have this function that's which is the log partition function, and then we subtract a linear function involving b. And since a is a strictly convex function, that means that the overall objective f, which is the negative log likelihood, is also strictly convex. And that's extremely useful in terms of developing properties. And in particular, we looked at 2 algorithms that we could use to minimize that objective. One is gradient descent, and we need to choose appropriate step size sequences to guarantee convergence. And then we had also had iterative reweighted least squares, which is kind of solving a different quadratic objective at each iteration, where kind of the weight matrix depends on the previous parameter. And so we found that that's an approach that we don't really need to choose choices of step sizes. And so in particular, for homework, you implement gradient descent, and the GLM function in R, and in particular the GLM function uses IRLS. So like the output should be the same because they should both converge to the maximum likelihood minimizer, because it's a convex objective, but the algorithms will be different. Okay, so today we focus on the fourth component of the framework, which is the statistical analysis. And so what that is we're trying to say, so we know that, so B is the true parameter. So what that is that, we know that yi is distributed P with the xi transpose B, and so B is the underlying true parameter. And then we want to say, beta hat ML is the maximum likelihood estimator, and so that depends on the data. So B is something that we don't typically observe. It's something that we're trying to kind of estimate from the data, because it's about the population. And so how do we how close are we actually getting to that? And so how close is beta hat ML to B, or B hat ML to B? Okay, and so we're going to consider two metrics which are very similar to metrics that we saw earlier. So we saw that mean squared error, and then we're going to look at the mean squared prediction error, which is okay, so here remember that the notation that x is in R to the n by p, where okay, so we're just borrowing some original kind of performance metrics that we saw in the case when we looked at linear models, which was the first module. So we had a 1 over n here, and so I'll just include that 1 over n here as well, to appropriately normalize things. Okay, and so what we're going to find here is that, as we saw, since we since we can't find upper bounds, instead of deriving the exact, we're going to derive upper bounds on MSE and MSPE. And this will also be under some conditions, which we'll see later. And I mean, what we're gonna see is, like, the main thing to kind of take out of this is just you know, that we're gonna see some results that look a little bit similar to what we saw for linear models. We have to worry a little bit about making sure that the variances of these are not too big or too small, and we'll kind of see why that's the case. Why that's the case shortly. Okay, so the key idea so we know from so a lot of the steps we're going to do is similar to what happened for the linear model, but now we're doing it in a more general setting. So so we're like, if you're kind of like lost in terms of what we're doing, just think back to what we did for the linear model, and this is in fact exactly the same thing. So remember that B ahead of ML satisfies that, you know, the gradient at of this negative log likelihood objective is 0, and the gradient here was okay. So this was the gradient, and so we have that. So this should just be this, because we're just deriving the general gradient here. This should just be this, and so therefore we have that. And so then we're going to do something that we kind of did in the case for the linear model, but we're going to, so we know that yi has this, you know, distribution P of xi transpose B, right? But the thing is now, this is not a linear model, but what we do know is that we know that expectation of yi is equal to A prime of xi transpose B. And then we also know that the variance of yi is equal to A double prime of xi transpose B. Okay, and so when we're deriving kind of mean squared error, we kind of only really need to worry about the mean and variances of these. So we can rewrite, we're going to use this kind of useful idea to say that yi can be expressed as A prime of xi transpose B plus some noise, epsilon I, where we know that expectation of epsilon I is equal to 0, and then we know that the variance of epsilon I is equal to A prime prime of xi transpose B. So you can think of this as it's like linear model, but both noise variance and sigma, and both noise variance and mean depend on B, and not in a linear way. So you can see that this is like you recover exactly the linear model. So for example, if we look at, a of theta equals half theta squared, which is the linear model, then you get a prime of theta equals theta, and a of theta, a prime prime of theta just equals 1. And so you just get that yi is equal to xi transpose b plus epsilon I, where epsilon I is, where, e of epsilon I equals 0, and variance of epsilon I equals 1. And so this is kind of one of these very nice examples where things generally sort of work out nicely, which was the linear model, which we already studied. But for example, if we look at, a of theta equals e to the theta, which is like, yi is Poisson, e to the xi transpose b, which was the Poisson model. We have that, yi is equal to e of xi transpose b, because plus epsilon I, where e of epsilon I equals 0, and the variance of epsilon I equals e to the xi transpose b. Okay, and you can do a similar calculation for the logistic model. So what's the point of doing all that? What that means is that we can then write so if we go back to what B hat ML satisfies, that's and since we can plug in we can just plug that right in, and so you end up with okay, so we've kind of got things now where it's starting to look like exactly the normal equations, but things are a little bit more difficult here because the a prime is not necessarily a linear function anymore, and the epsilon I has a variance that also potentially depends on b. So we're, as we'll see later, we're not going to be able to get exact expressions, but we can get something where if we make some assumptions that that we can get some pretty nice upper bounds that look very much like what we got in the linear model case. Okay, so so now we use Taylor expansion slash the mean value theorem. We're going to kind of use it in a similar way to what we did for the proof of grade, like what we did when we kind of derived the updates for gradient descent, to kind of try to convert it into a linear type of expression. So we know that a prime of we can re-express that as a prime prime of some argument. It doesn't really matter what it is. We know that it's there is such a value, and then that's going to be times okay. So we're essentially just expanding this this out using kind of the mean value theorem, and so gamma I here is just somewhere between Okay. And so then we can kind of write this out as okay. So now this is where we're going to kind of make some important assumptions here. So we're going to assume that the variance a prime prime of gamma of I, not to. So remember that the double derivative relates to the variance, and so this should not be too big or small. Okay, and so we'll sort of see where that comes into play, because what that then means is that we can say that so we can write. It's convenient to write this out in matrix vector form as follows, as we've done before. So this can be written as so remember that x is in R to the n by p, and w is going to be in R to the n by n, and it's a diagonal matrix where wii just equals to a prime prime of and since we have this condition that and this should be true for all I. A natural question you might ask is this condition going to be satisfied? And in many cases it is, as long as kind of you know that the estimate is not kind of too doesn't get sort of too crazy. So this is often a reasonable assumption that's made. It's basically ensuring that the variance of your y doesn't get too big or too small. And so since we have that is greater than CL for we can say that the matrix W is greater than or equal to CL times the identity, right? So this is the identity matrix, and therefore we can say that okay. So we can kind of argue, I'm not doing this super rigorously, that therefore we have that okay, so we can kind of remove that W. And again, I'm not being overly rigorous here. Yeah, I just wanted to give you an idea of how this works. So then we can say that okay. And further, since we have that okay, we're also going to have that it's less than or equal to Cu. Sorry, this should be 1 over Cl. And so we can say that then we can say that so Z where okay, and so again, I'm not being overly rigorous. I'm just kind of giving you a flavor of how these kinds of analysis arguments work. We can say that okay, so what we're going to get is something very similar to what we had for the okay, and since E of Z transpose equals to the identity because it's they're independent zero they're independent and they're zero mean. Then we have that and in fact it should be the um, and I'm just gonna kind of go just explain the expression at the end because it's not critical that you get all the steps, but then we can kind of, in the case where we have the main thing that we'll go through is kind of the understanding behind this. Then and then there's a 1 over n here, and so we end up with okay. So yeah, I haven't been very rigorous here. The main point to take out of this is that so for the standard linear model, the result is exact. The result is exact, and we also have that, and we don't have the balance cu squared over cl squared, which is the ratio of smallest to largest variance. Okay, so another way to think about it is if you looked at kind of the weighted least squares type of approach, when you don't have the same variances, you kind of can't quite derive as good an expression, and that's exactly kind of what we're getting here. Like you have this bound which relates the ratio of the maximum and the minimum variance. This gives just an idea or flavor of how to relate B hat ML to B. Since we're dealing with a GLM, nonlinear equations make it very difficult to obtain exact closed form expressions. Okay, so this is not something that you're going to have to do in the homework. I just wanted to kind of show you how it's done, sort of roughly, just so you can get an idea of how you might relate the maximum likelihood estimate to the true parameter, because that was not something we'd really covered yet in the that was not something we'd really covered it covered earlier on, and so. And another thing to mention is that we don't know the exact distribution of B hat ML, but as n goes to infinity, we can derive asymptotic distributions. Like in the linear model case. Okay, so that was kind of all that I wanted to say about the analysis component of the GLM, and you know how we find you know how do we show how close beta hat ML is to B. So so that should kind of tell you everything that we covered in today and the previous 4 or 5 lectures should be enough to provide you with a starting point for the second homework. So now we're kind of moving on to the third module. So the third module or topic, and that's this idea of, so this is regularization. And in particular, we're going to focus on two types of regularization that are very widely used in statistics. We're going to talk about, ridge regression, which is, where you use kind of a smoothness or an L2 type of regularization, and I'll be clear about what that is, and lasso or L1 regularization. And so, I mean, when you hear that term regularization, you kind of may have no idea sort of what it actually means, and that's fair enough. We're just gonna we're gonna kind of get a sense of what that is slowly as we build up to it, and see a couple of concrete examples which we'll go into detail in. And this is going to lead to algorithms. So, before kind of moving to the statistical framework, I'll just kind of present the basic idea. So the basic idea is that so far we've kind of focused on estimation schemes related to maximum likelihood, but okay, so far we've mainly focused on kind of maximum likelihood estimation types of approaches. So least squares is the maximum likelihood estimation approach when you have Gaussian data, and then we saw that when we had generalized linear models that maximum likelihood estimation was a pretty typical kind of approach. But maximum likelihood estimates are good, and they work particularly well if the number of parameters that you're dealing with P, so P is the number of parameters or variables in your data, if that's relatively low. But it turns out that we're talking about multivariate statistics in this class, and so the number of variables could be quite large, like even 10 may be large, but hundreds or even thousands. And so in that case, maximum likelihood actually often runs into issues. So in particular, one issue is that maximum likelihood tends to kind of overfit the data, because when you have large numbers of parameters, that actually kind of means that your mod the size of your model also gets quite large, and that tends to overfit the data because you're fitting a very complicated model to the data. The other thing is that if your variables are highly dependent or correlated, these methods are like the maximum likelihood estimates often unstable, and we're actually going to kind of see examples of this through a particular when we in particular see the two regularization schemes that we're going to focus on in this course. And the other thing which it often does is that you might have some prior information. Like you might say that, okay, there's 1,000 features in the data, but only 10 of them are really going to be relevant. And maximum likelihood doesn't really account for that. And so is there some way we can account for that? And so regularization addresses these three major issues or challenges. Okay. So let's now let's move on to the so we're going to look at the statistical framework. So we're again still in the supervised setting. So we have our data. So we're supervised, so there should be a Y there. Okay, and then we're again going to kind of use this notation that, this vector notation. So nothing's going to change in terms of the statistical model. We're still going to kind of assume that so P belongs to natural parameter exponential family, as we've already seen. So nothing really changes in terms of the first two components of the model. But what does change is the third component. So in this case, what we're going to do is we're going to use regularized. Another way to think of it is penalized maximum likelihood. Okay, so this is going to really be what we're going to talk about today, at the end of today, and then going into the next couple of lectures. And then we'll move on to the analysis later, but we'll focus now on the general estimation procedure. Okay, so this is the negative log likelihood objective. This is the negative log likelihood that we've already seen. So this could be, for example, least squares, the GLM objective that we've already kind of seen, that we've so far tried to minimize. And so in the past, that's what we've generally tried to minimize, is that expression there. In the regularization case, we're actually minimizing is this plus another term, and so this is really the regularization. And let me talk a little bit about this shortly. So lambda here is the regularization parameter. So, an R of B here, which is a function of the parameter B, that's the regularization slash penalization of B. Okay, and so let's just think, I'm going to sort of talk a little bit about this. So lambda really tunes how much regularization we do. And in particular, so far we've looked at the case lambda equals 0. Okay, and so what we're going to do now is to kind of say that let's let lambda be bigger than 0, and there's going to be some regularization that we're trying to induce here. And so just to give you an intuitive idea of what's going on relative to what we've spoken about. So the idea is that, remember that I talked about bias and variance of estimates, and the kind of intuitive and high level idea is that lambda kind of trades off bias and I'm putting these in quotations because that's not, like, the notion of bias and variance is a bit more difficult to talk about when you move to generalized linear models compared to the linear model. But this is just kind of the general idea. So, if lambda equals 0, you have, 0 or small bias. Remember that, in the case of least squares, you found that was an unbiased estimate because that was corresponding to lambda equals 0. And then we'll see, but large variance. So, and again, these are all intuitive ideas. We're actually going to see how this exactly works in a particular case. So making lambda bigger than 0 increases bias, but reduces variance. Which potentially lowers the MSE or MSP. Okay, so we're gonna focus on two concrete regularization terms. So one is that this is going to be the 2 norms squared, which is just Okay, and so this corresponds exactly to ridge regression. It's sometimes referred to. It's also extremely sort of famous and widely used. So it's used. It's also sometimes referred to as Tikhonov regularization. And the second one, which we're going to see, is the L1 norm. So that what that is just you sum up the absolute values of BG, and this is referred to as often like lasso regression. And this is also, that has many names, but you can also think of it as just naturally L1 regularization. The next couple of lectures will focus on one, and then okay, so we're gonna get into some more details. In the next lecture, but the last thing I just wanted to comment on before we move on is that. So now we're going to kind of refer to this from the estimation point of view. So we know that we're going to think about this from an algorithm point of view. Sorry, this should have a yi and a p of xi transpose b in it. So let me just change that up here as well. I'm going to use the term beta hat r for the ridge estimator. And then I'm going to use b hat l for the lasso estimator. Okay, so one thing to bear in mind here is that remember that because we're in a generalized linear model setting, this is just okay, and we know that A is strictly convex. And so the question is So, does beta the ridge estimate and the lasso estimate exist, and are they unique? So it turns out that because A is strictly convex, we know that, so you can tell that, or it's easy to check that norm of B squared is strictly convex. And then the norm of B, the L1 norm, is convex, but not strictly convex. And so why is this the case? And I mean, if we look at the case where P equals 1, if you kind of draw them, then you see that norm of B squared, which is just B squared, so this is clearly convex or strictly convex. Was just whereas on the other hand, if we plot the absolute value, this is convex, but not differentiable or strictly convex. Okay. I'll talk about that in a bit more detail. The L1 kind of, the L1 norm is a little bit more complicated to deal with than the L2 squared norm, and we'll sort of talk about how we deal with that in a couple of lectures. But the upshot of that is that so we know that beta hat R is a minimizer of a strictly convex function. And that's if lambda is bigger than 0, because if it's 0, then obviously, you can potentially have, the least squares, it only has unique solutions if the rank of x equals p. But if lambda is bigger than 0, it's always going to is the minimizer of a strictly convex function, and this is therefore beta hat R exists and is unique. And we know that beta hat L is minimizer of a convex function. Beta L exists, and we can say more than that, that, any local minimizer is also a global minimizer. Okay, so there's many algorithms that exist that can actually find these. They're not kind of impossible computational problems. We're going to kind of see some of those in the next few lectures. But this is kind of the reason why these are probably two of the more popular regularizers that people use. That because both the squared L2 and the L1 penalty are strictly convex, or the L2 penalty is strictly convex, and the L1 is convex but not strictly convex, and so there's a whole suite of algorithms we can use because of this kind of nice convexity property that we have, and we're going to go into this in a lot more detail in the next couple of lectures. Okay, thanks. That's it for today.